Good morning, everyone, and welcome for the new TMS meeting. Today, I am really pleased to introduce you Dr. Andrea Lazzarini, who will talk about heterogeneous catalysis. Just a few words to introduce Andrea. Andrea Lazzarini obtained his master's degree in material science in 2013 at the University of Torino. In the same university, he got his PhD in chemicals and material science in 2017 under the supervision of Professoressa Elena Groppo and Professor Carlo Lamberti with a thesis project entitled The Structural and Surface Study of Metal Nanoparticles, Based Catalyst and Relative Supports, focused on the study of carbonaceous supports for catalysis and evaluating their role in the catalytic process. Due to the results obtained during this period, he obtained the ISIS Impact Award 2018 Economic Award, awarded by the Science and Technology Facility Council of the United Kingdom. Then, for 2 years, he worked at the chemistry department of the University of Oslo under the supervision of Professor Unni Olsby and Professoressa Silvia Bordiga, studying and developing metal-organic frameworks-based catalysts for the catalytic reduction of carbon dioxide to methanol and for ethylene dimerization. Due to the results obtained in his career in the field of gas-phase heterogeneous catalysis, he obtained in this year the prize Robert Carl Grasselli in honor of Professor Carl Grasselli, awarded by the Catalysis Group of the Italian Chemical Society. The last year, since the month of October, he joined the research group, my research group in dell'Aquila University, working on the heterogenization of organometallic catalysts for the study of selective oxidation reaction in liquid phase by using a functional magnetic nanoparticle support. The project is still ongoing. It's clear that the topic of the talk of Andrea Lazzarini is dedicated to catalysis. Catalysis is a very important field of research, and especially represent one of the 12 principles of green chemistry that clearly state that the use of catalyst instead of stoichiometric reagents is a very important point to reduce the environmental impact of chemical processes, minimizing the waste and the production of pollutant products. The title of the talk of Andrea is The Importance of Being Supportive when supports help heterogeneous catalysts in their work. So he will try to illustrate us the reasons that are behind the choice of heterogeneous support. Now, I am really happy to give the floor to Andrea for his speech.
Thank you very much, Marcello, for your really kind and very appreciated introduction. So I will happily share my screen. Okay. Here. Okay. So, as Professor Crucianelli already anticipated, my presentation is focused on the role that the supports for heterogeneous catalysts have in the total catalytic activity of the system that is employed to develop chemical reaction. So, as Professor Crucianelli already said, catalysis is a fundamental field in the modern chemistry. So, first of all, I will try to give a very simple definition of catalysis. If you look at the Oxford Dictionary, at the voice catalysis, you will find that catalysis is defined as a process of making a chemical reaction happen more quickly by using a catalyst. So now it's natural to define a catalyst as a substance that causes or accelerates a chemical reaction without itself being changed. So it's exactly a substance that is promoting a chemical reaction without changing. So it cannot be defined as a reactant or a product. It's something that is helping the products to become reagents to become products by changing the activation barrier of the processes. Principally, there are two kinds of catalysts that can be defined by their physical nature. Homogeneous catalysts that are present in the same phase as reactants. So usually the reactant can be gaseous, solid, or liquid phase, but generally the more homogeneous system that can be found for catalysis is liquid phase. So the catalyst is itself either a liquid or soluble in the liquid phase, where also the reactants are soluble. Therefore, there is a very strong interaction and contact between all the phases, the reactants and the catalysts. Another possibility is that the catalyst is not soluble in the phase where the reactants are present. That can be either gaseous or liquid phase. And usually these kind of catalysts are solids. So what can be done is to suspend the solid powder inside the gas phase or the liquid phase by maintaining a very strong and continuous agitation, so that we can spread all the catalyst inside the phase of reaction to maintain a very high contact. So both kinds of catalysis are appreciated and very exploited, and they present both drawbacks and advantages. The main advantage of homogeneous catalysis is that since all the reactants and the catalysts are in the same phase, you have the highest contact possible between all the elements of the reaction. The main advantage of heterogeneous catalysis is their easy of recoverability, because once you remove the phase in which reactants and products are dissolved, you can more easily recover the catalyst that can be reactivated or directly reused, reemployed in a second step of reaction. So the drawbacks, as you can imagine, is for the homogeneous phase is that you have a difficult, if not impossible, separation between the catalyst and the reaction phase, which made them not be reusable often as catalysts. Heterogeneous catalysts, in general, they show lower activity than the homogeneous counterpart, just because having two different phases, you have a reduced contact possible between the active phase of the catalyst and the reaction environment. So, since I was focusing all my career until now on heterogeneous catalysts, we can divide these catalysts into two big categories, supported and unsupported. Starting with the unsupported ones, we can define the unsupported catalyst when the substance or the material itself is employed as a catalyst, without any employ of further functionalizations or active phases. And the biggest example of this category of catalysts are zeolites. Zeolites can be either natural. They come from the Greek word that stands for stones that produces vapor, because they are naturally produced, especially in volcanic eruptions, and they can trap easily water, and so when they were heated up, they were releasing steam. So they are basically silicates made of silicon oxygen tetrahedra intercalated by aluminum oxygen tetrahedra. And you can make several possible geometrical forms in which you can define different units. As you can see, you can, you can have different disposition of the tetrahedra to make different shapes. And when you have different shapes, you have different cavities that can produce different lattices. So depending on which kind of units you link together, you can have many and many. Usually there are hundreds of this kind of catalysts that can vary in their shape of the cavities and the amount of silicon and aluminum present in the structure. Zeolites, having the introduction of aluminum oxygen tetrahedra inside the structure, they present naturally acidity, because aluminum has a lower positive charge than silicon. Therefore, being surrounded by all oxygen atoms, it's carrying a negative relative charge that is usually counterbalanced by protons. These kind of protons make the activity of zeolites, because they are used as acid catalysts. So what is important to regulate the acidity of the zeolite is the silicon-aluminum ratio. So the higher is the aluminum present inside the lattice, and then the lower is the value of the silicon-aluminum ratio, the higher is the acidity of the zeolite. Apart from zeolite that can be unsupported, we have supported catalysts. This means that the support that we are employing is not the material that is active in the catalysis. And again, one of the examples, the more famous examples of these supported catalysts can be, again, zeolites, because as I told you before, they naturally present a proton to counterbalance the the relative negative charge inside the lattice, but it can be easily exchanged with metal ions that can act as redox catalysts. So the zeolite itself, that was bearing the proton and so being itself the catalyst, now is an active support that is able to capture and trap these metal cations that can perform redox catalysis. And so again, we define the silicon-aluminum ratio. This time, instead of the acidity, if we have a higher presence of aluminum inside the lattice of the zeolite, we can have a higher metal loading. That means a higher activity of the zeolite. But this is not the only possibility to introduce a functionality inside the zeolite. Being a silicate, it can be produced a catalyst by grafting a metal organic moiety onto the surface of the zeolite by different chemical reaction by surface organometallic chemistry. They can be grafted and anchored to produce an heterogeneous catalyst where the metallic phase that is loaded onto the surface of the zeolite can be the active phase. And they can also be bifunctional catalysis, in which you can have a metal loading outside that is performing redox chemistry, and you can have still an acid catalyst by continuing to carry the protons inside the lattice of the zeolite. But of course, zeolites are not the most employed supported catalysts. Probably the most famous ones are metal nanoparticles. Metal nanoparticles can be either dispersed in a colloidal way inside an homogeneous, let's say in a solid, in a liquid phase, but mostly they are supported on some kind of supports that usually are oxides, like, again, alumina or silica. The idea of, again, supporting metal nanoparticles onto some kind of support is because compared to the colloidal system, In the liquid phase, you can have a more robust system because you, in this way, you kind of protect the nanoparticles from the coalescence phenomena, so the particles are growing together, so you reduce the surface area of the catalyst until its deactivation. You can again couple the high activity of metal surfaces with the high surface area of the nanoparticles, and this way you can guarantee a higher contact between the active phase and the reactants. And also, you can name the metal, you can name the support. You have an extremely high tunability in the metals that you can employ to produce the nanoparticles for catalysis, and the choice of the support that is employed, and is exactly this part that is exploited for supported nanoparticles catalysts. But again, not all the supports, not all the materials can be employed as supports. There are some supports for the choice some rules for the choice of the support. And I like to call them like an old way and a modern way. So the old way is that the support should have high thermal and chemical stability. Of course, because it has to sustain the conditions that are present in the reaction environment. It should have a reduced interference between the support and the active phase and the reaction environment in order not to modify or let's say have some detrimental effect on the reaction. And it should guarantee a high surface area. Of course, these are the classical rules. I like to call to name new rules for modern supported catalysts that can be represented in these 2 points. Of course, the first point is respecting rule 1 and 3, because still you have to maintain the thermal and chemical stability of the system in the reaction environment, and still you have to guarantee a high surface area value to maintain good contact between the active phase of the catalyst and the reaction environment. But also they can be chosen in a way that they can promote synergistic effects with the active phase or the reactants in order to enhance the activity of the reaction itself. But of course, in order to choose the right support for your catalyst, you should go through a very deep characterization of the supports. And the main characterization methodologies are, of course, physical-chemical techniques. Some of them, like nitrogen physisorption and microscopies, can provide some textural properties on the catalyst by determining the surface area and the morphology of the materials. Then you have some techniques that can provide structural informations, like diffraction if you have a crystalline material, or TGA if you have an organometallics, for example, to determine the amount of functionalization on the surface. And then some other techniques that are very important, since catalysis is made of surface interaction, like chemical titration, infrared, neutron spectroscopy, and X-ray spectroscopies, photoelectron spectroscopy, and X-ray absorption spectroscopies. So these techniques were present throughout all my career, and they were very useful in performing all in obtaining all the results that I got during all my working period. So having given you this small introduction about catalysis and how can the supports be characterized for an heterogeneous catalyst, I will go through a bit of my personal experience that went mainly through these 3 kinds of supports that were employed to produce heterogeneous catalysts. The first one is activated carbons that are carbonaceous materials that I studied when I was in Turin, metal organic frameworks that I was developing and studying when I was in the University of Oslo in Norway, and some few ideas on the system that I'm working on now. So I will start with activated carbons. Activated carbons cannot, they might look not very interesting from, let's say, macroscopic point of view, because they are black, they are dirty, they are powdery, they fly everywhere. But if you can go a bit deeper and if you get to know them a bit better, you can imagine a single grain of this dusty powder as an ensemble of different sheets made of hexagons that are characteristics of the graphite structure that are basically disposed in a random way throughout the grain. And what is interesting is that going to this intermediate scale, to the nanoscale, so going to study each single of these sheets of graphite/graphene, you can see that you can have a very large variety of functional groups and structural defects. So I was working mainly on activated carbons produced by pine wood, so basically ashes of trees. As you can see, in this picture, it's still possible to observe the walls between the cells that were composing the lignin structure of the tree. And these two carbons, they come basically from the same kind of vegetable, but they were treated in different way. One was impregnated with phosphoric acid, and one was treated in steam at high temperature, basically 1000 degrees in the absence of oxygen. They present very similar granulometry of the particles, and they have both high surface area value. With this, they were produced 5% weight palladium nanoparticles, catalysts these particles were deposited onto the surface of these carbons. So my goal was to characterize thoroughly these two systems and to see if the differences among them, they can provide explanation for different catalytic activities. So being carbon black and difficult to study with spectroscopies based on light, the natural choice was using neutron spectroscopy. That is sensitive mostly on and only on the hydrogen terminations that are present in the systems. So as you can see, they look pretty much the same. Of course, the intensity is different because of the surface area difference, because having a higher surface, this means that you have a higher number of hydrogen atoms. So they have same bands and different intensities, especially in this particular spectral region. That is the most one that give us the information on the terminal hydrogens on the different borders, which can be more ordered or more disordered. So we simulated, for example, a small fraction of condensed aromatic rings that can be, let's say, compared to one of these sheets made of benzene rings. So we found that this kind of signal was given by very regular borders, while the signal coming at higher energy was fundamentally coming from more disordered borders. Therefore, by comparing the intensities of the relative intensity of these different bands, we could have an idea on which kind of carbon was more regular or irregular on the surface. But this was concerning just the effect that the different hydrogen terminations can have. One other possibility was to study with other spectroscopy, infrared, Raman, and X-ray photoelectron spectroscopy, the effect of functional groups. And in fact, all the spectroscopies, they were, let's say, highlighting a difference among the two samples by having a different oxygen content. And this was coming from different functional groups like esters or acid groups or aldehydes, lactones. And this was having an effect, a tremendous effect on the nature of the catalyst itself. So these two guys have not only different hydrogen terminations, but also different amount and type of oxygenated terminal groups. So if we come back to our two carbons, we made 5% palladium on carbon catalysts on these two, and we tested for hydrogenation reactions. But while the first catalyst was very active for hydrogenation reaction of the benzene ring. The second one was more active in the debenzylation reaction by cutting this carbon-hydrogen bond here, carbon-nitrogen bond here. And the explanation that we gave is that being these catalysts more having less surface as having less functional groups and more extended and regular graphene-like character, it was able to physisorb with pi interaction the benzene rings, let it travel towards the active phase, then on the surface of the nanoparticles made the magic of the catalysis happen, and then once you don't have any more the pi interaction, release the products. While in this case we have a less regular carbon with more oxygenated groups. Therefore, it was less prone to let these two aromatic rings absorb on the surface and perform the hydrogenation reaction on the rings and favoring the debenzylation reaction instead. So, by studying the nature of the support for our catalyst, we could state that the same active phase that is deposited on different supports can lead to very different catalytic properties. Following this topic, I was working on metal organic frameworks, again as a support for heterogeneous catalysts. But since activated carbons are probably more commonly known to everyone, I will just give you a small introduction of what is a metal organic framework. So basically, metal organic framework is a crystalline solid that is made of a metal node. In the case that I was using the MOF with this kind of structure, UIO67, that was developed in the University of Oslo, and they are zirconium-based MOFs. So basically you have a zirconium metal node in which you have some linkers that are linking among all the different nodes, and they are biphenyl rings with two carboxylate groups that are attaching to the zirconium node. And then when you couple them together, you can end up with a very ordered and with an extremely high surface structure. So classically, the UO67 framework is made just by pure biphenyl rings that are linking the zirconium nodes. But in our case, we developed a structure where bipyridine rings can be isosubstituted, since they have the same steric hindrance in the structure. You can change 10%, up to 10% of the linkers with bipyridine rings, and the two nitrogen atoms can provide the anchoring point to graft a metal ion in order to perform catalysis. So our case, we were loading palladium and platinum mostly, and we were interested not only in the grafting of the metal ion inside, on the bipyridine ring, but also we were interested in the shape and the size of the cavity, because as you can see, this is a very large space in which you can trap a metal nanoparticle, and these holes inside the structure of the MOF, these cavities can hide as a templating agent for the metal nanoparticles in order to provide a very specific size of the particles. As I told you, metal organic frameworks are crystalline. As you can see, you have by diffraction, you can have an idea that having several very sharp peaks, you have a very crystalline material. And by performing nitrogen adsorption, as I told you before, we reached a surface area that is close to 2,400 square meter per gram. So having 1 gram of this sample, you have several hundreds of surface available to deposit your active phase. And even after the functionalization with the platinum chloride species on the bipyridine ring, we maintain a very crystalline system and very high surface area. The only weak point of these materials is that since are hybrid in nature, so they have both metal and organic parts, they can be weak from the temperature point of view. As you can see by the thermogravimetric analysis, we were heating the metallogram, the UA067 systems in air, and after a certain point, they started to degrade and lose all the organic parts and becoming basically zirconia. So we decided to keep our temperature limit to 350 degrees in order to save our material in the reaction. So for this kind of systems, I was testing our material in an operandi way by performing infrared and X-ray absorption spectroscopy. This is the case of infrared, where we have the material under analysis and we were feeding the reactants, basically CO2 and hydrogen, to the system, and we were monitoring contemporarily the products by means of a GC system and also the infrared evolution of the catalyst. And as you can see, by sending CO and hydrogen, we can have plenty of different reactions that can happen to our system. Basically, we were interested in the ones that were producing the highest added value molecules, such as formaldehyde and methanol. To do so, we were testing either the platinum MOF system and the platinum silica system. And as you can see, the platinum MOF, after activation and forming nanoparticles with the size of almost 2 nanometers, it was a bit more active than the traditional platinum on silica system, meaning that the MOF somehow can have some impact onto the catalysis. But unluckily, what we were doing was just doing the reaction number 1. So we were producing carbon monoxide from carbon dioxide, so not a very interested system for this kind of reaction. So in order to check what is the system, the mechanism, the reaction mechanism that is producing CO, we were trying to make some isotopic exchange experiments. So instead of using hydrogen as the reducing agent, we were using deuterium. So basically it's just hydrogen with a neutron more. So it has exactly the same chemical properties, but a different weight and mostly a different infrared signal. And therefore, we checked with the GC system what was happening to the system, and basically we were ending up with just CO and few, let's say, molecules of methanol and methane. But then, when we started to dose, sorry, forget about it. And when we were dosing exactly CO2 and hydrogen, we were forming basically CO that was absorbing on the metal nanoparticles, giving an infrared signal, which is typical for CO absorbed on metal nanoparticles, which is in this spectral area. But we were also observing the formation of small bridged formate species that was giving a very extremely tiny signal. As you can see, it's like 50 times lower than this one. But then when we exchanged the feed with deuterium, what happened was that we observed a dramatic increase in the methanol production. And the explanation that we gave was that we were basically increasing the amount of this formate species. As you can see, this very tiny signal that was here that is shifting because deuterium is heavier, and so you need it's shifting the signal to lower energies, and you see the intensity of the signal is hundreds of times more intense. That is justifying the increase of the production of methanol. And what we ended up was that these formate species that are forming at the node and the platinum nanoparticle interface are the ones that are responsible for the formation of methanol. And we tested also, we characterized the material after reaction, and we ended up with a slight lower surface area because, of course, we have some degradation of the material, and mostly we have filled the cavities of the MOF with some metal nanoparticles that are reducing the surface area, as you can see from these microscopy images. But still, the system was cycled and was still active. And so this was a very good discovery from the group where I was working in. And now, just a few words about magnetic nanoparticle systems. I will be very quick on this part, since it's still under development. So we were doing basically nanoparticles that can be magnetically recovered. So this means that when you have a reaction environment and you stop the steering, the magnetic steering, and you go close with the magnet, you wait some minutes, and basically you can recover your catalyst in this way. So you can remove the liquid phase, and by not even removing from the vial where you are performing your reaction, you can recover the catalyst, and it's already ready for the next cycle. But itself, the magnetic nanoparticles and the magnetic fields, it's very fun. You can do a lot of things with the magnetic nanoparticles, but if you don't cover them with something, they might, let's say, interfere with the catalysis that is your final goal. For these reasons, we were covering our particles with the silica, which, as I told you before, provides a very nice shielding, and it's inert to mostly all reaction environment. And also it's easy for it to provide an anchoring point for further functionalization of the active phase. So basically we were producing magnetic nanoparticles covering with silica, and then functionalizing with organosilanes that are able to be to undergo further functionalization with any kind of anchoring molecule. And once you have performed, you have produced your anchoring point, that is this point between the nitrogen and the oxygen that can vary different metals. You can graft and anchor different moieties like molybdenum, tungsten, vanadium, and you can go through oxidation of different substrates that can be olefins, that can be terpenes, you name it, you can do it, sulfides, and you can obtain oxygenated products of these species. But I don't want to give you too much away, because there will be another conference next Thursday. I will present a deeper, let's say, study on these systems. So for the people that are interested in, I just make some advertisement. Next week on the 16th of December at 12:30 in the afternoon, there will be a presentation of me more detailed on this kind of systems. So, in order to conclude, we can say that the choice of a specific support for catalysis must always be backed by a complete characterization, because without it, you don't know which is the material that you are employing for your catalysis. Then catalytic testing should always be performed with active and non-active supports, because as you can see, without comparing the catalytic activity, as I showed you before, between the MOF and the traditional support, you could not underline its higher activity towards the wanted reaction. And again, the only limit to design a supported heterogeneous catalyst is your imagination, because you have a whole bunch of elements. You have the whole periodic table, whole transition metal lines that you can choose for your catalyst, and you can play with oxides and all the other substances to produce an heterogeneous catalyst. Before closing and thanking you all for your very kind attention, I just want to acknowledge the people that were helping in my work in the past, Professor Elena Groppo and Carlo Ramberti and all my co-workers in Torino, Professor Juni Olsby and Silvia Bordiga and all my colleagues that I left in Norway, and also Marcello Crucianelli, Roberta Colaiezzi, that is working with me on this topic, and all other my colleagues from University of L'Aquila. And again, thank you for your kind attention. And of course, I am available for any questions that you want to ask me. Thank you.
Now we can open the questions time. Thank you very much, Andrea, for your rich, exhaustive and very interesting presentation. And I can read one question from the chat. What is the advantage of using magnetic silica beads rather than just functionalizing silica on a solid support? For example, could you make a functionalized silica capillary through which you can make your reagents flow and get the product out?
Okay, this is a very good and interesting question. Of course, a capillary is made of silica, and of course, as the silica beads, they can be functionalized with organosilanes. The point is that using beads, or better nanoparticles, you have a much higher surface contact between your reagents and your final catalyst, because you can imagine the size of a capillary is the surface you can imagine is few square centimeters, while when you have these kind of systems, you have around 100 square meter per gram. So using a gram of this catalyst, which is more or less the weight of a capillary, you can have, let's say, 1,000 times higher surface contact for your active phase. And again, using nanoparticles, you can imagine that removing them can be sometimes difficult, because you have very small particles that can clog your filters if you want to separate them. They are maybe difficult to be centrifuged away, but by using a magnetic core, it's really easy. You just use a magnet, you come close to your system, and in few seconds, all the particles are coming attached to the walls of your container where the magnet is standing. And then you have almost clean, let's say, liquid phase of your reaction that you can remove, and you can analyze and check your products. And it's much more simple and quick, very time saving. I hope it was an exhaustive explanation.
I think so. No other question in the chat. Please, I invite all participants to make some question regarding this talk. But one insight from me, Andrea, regarding the two main drawbacks of heterogeneous catalysis, that is the leaching of the active metal species, yes. And especially in the case of a gas phase reaction, the sintering. That is the merging of yes. Small active particle to form a bigger particle and then reducing the surface area. What do you think yes. about these drawbacks?
Yes. Yes. Concerning the sintering, it's the idea of using an active support can also be the one of helping the particles to keep their stability. Of course, if you're talking about an active phase, usually the conditions for your catalysis are quite harsh. So you go up in temperature to hundreds of degrees, like 500–600 degrees, and you have strong oxidizing environment or strongly reducing environment, and all these tend to let all the particles to agglomerate. And so this is unavoidable for any supported catalyst. And again, for liquid phase catalysis, leaching, sometimes it can be dramatic also, because if you don't keep it into account, you might think, okay, I'm recovering my catalyst, but then you don't have any more active phase that remained in the reaction environment, so you are not aware of this problem, and you have to be careful on this as well. So it's true, these are the two main drawbacks.
Yes. Okay. And thank you very much again, Andrea, for your interesting talk. I am not able to see other questions from the chat. Thank you all for sharing at this interesting conference. And now I think it's up to Marco for the last remarks.
Yes, thank you both for this very interesting talk. It was really very rich in content. So thank you, Andrea, and thank you, Professor Cuccianelli, for the moderation.
Marco, I guess we have a question. I see a raising hand. Or some remarks.
No, I don't see it.
No,
no,
it's not a question. I let Marco to finish, and then I have to make an announcement.
Oh, I'm sorry.
Is the announcement about Monday?
Exactly.
Okay,
so
then you go
and I can continue. So go ahead.
Okay, so next week is a very special week for the TMS because we have two events. And one is an extraordinary event which will be held on Monday. So Professor Tetti will talk about this and introduce the extraordinary TMS that will be held on Monday at 2. So please go ahead, Professor.
Yes, thank you. Before that, I have to say that being not an expert in the field, I have no special questions for you, but I want to congratulate you because the presentation was very clear, and I think it was really enjoyable. But my studies in chemistry, in organic chemistry, are dated back many years, so sorry about that. In any case, following up actually the nice presentation that we just heard, this special event will be presented by an eminent scientist. He's a nephrologist based in Germany. His name is Jürgen Flög, but the presentation will be on, the title is How to Ruin Your Presentation. Because, the speaker today was really very good, but not always this is the case, no matter if you are a student or a big scientist, this happens. So Jürgen will talk about that, and I recommend everybody to participate, from the students, undergraduate students, because it's a way for you to learn how to manage your data, and going on to the PhD students, postdocs, and also experienced scientists. So I really recommend this to everybody. And I expect the presentation be also a little bit fun. So let's see how it goes. So don't forget that it is on Monday, and it's at 2 o'clock, not 1:30. This was because Professor Flög was not available in other dates. Sometimes we make this kind of exception for eminent scientists. So, okay, that's it. Thank you.
Okay, that's great. Thank you, Professor Tetti, for the announcement and also sharing the flyer. So you can take a screenshot, but we will send this out. It's already on the social media, so you can share it if you want. Tell your friends. It's interesting for everyone, even for people who are not scientists, because it's nice to know how to convey your message in general. So in addition to this, we also have the regular TMS on Thursday. So don't forget also about that. And we have a journal club by the Biotechnology Journal Club and this is the regular time, regular date on Thursday. So 2 events next week, one on Monday, one on Thursday. Yeah, I think this is it. We also decided to do 2 events because, of course, we are not going to have a TMS on the 24th of December and the 31st. So we tried to match more events in 1 week. I hope you will enjoy this. Okay, so thank you very much.
Yes, let me say also to Andrea and Marcello, this group is really heterogeneous, so it's interdisciplinary, and as you see, we have a good crowd of people attending, and some of them are not based in L'Aquila; they are based even outside Italy. So it's a good way if you have guests, if you have topics that you want to share, to use this system for that, because I mean, and just suggest topics, suggest speakers. Actually, if Andrea wants to contribute to the TMS, there is room in our committees to do that. So just discuss with Marco, and we need ideas. We need people just making suggestions, and it's a good way for everybody to have the audience quite large and interested. So it's just an invitation to contribute if you like.
If we will have some good, let's say, topics and people to invite, we will for sure let you know.
Okay, thank you. Okay, Marco, you can close.
We already recruited half of the Department of Chemistry, so we have to take everyone now. That's the end game. Okay, so thank you very much, everyone, for being here. It was a very well attended seminar. We had more than 80 people connected. So see you on Monday. Thank you very much.
Bye-bye.
Thank you.
Thank you.